Hey everyone, and welcome to this explainer. I'm going to walk you through exactly what you need to know about ionic bonding so you can absolutely ace your upcoming chemistry exams. Whether you're reviewing this for the first time or maybe cramming right before a big test, my goal today is to be your personal lecturer. We're going to break down the core theory, look at the exact diagrams examiners want to see, and highlight those classic traps that always seem to cost students marks. Let's get you that top grade. Here's a quick look at our agenda today. We'll hit Section 1, why atoms form bonds, then Section 2, forming cations and anions, Section 3, the ionic lattice structure, Section 4, dot and cross diagrams, and finally, Section 5, tackling exam questions. All right, let's jump right in with Section 1, why atoms form bonds. To really get chemistry, you have to understand the fundamental motivation of an atom. Simply put, they just want to be stable. So the crucial point here is that atoms are generally pretty unhappy unless their outer electron shells are completely full. If you look at the noble gases on the far right of the periodic table, they already have this perfect full outer shell, which is sometimes called an octet. And because they're already perfectly stable, they just don't react. Every other element on the periodic table is essentially jealous of this. They strive to achieve this noble gas electronic configuration, and they will trade, steal, or share electrons just to get to that highly stable state. That deep desire for a full outer shell leads us directly to ionic bonding. Ionic bonding happens specifically when metals, which are the guys generally found on the left side of the periodic table, transfer their electrons to nonmetals on the right side. When this transfer happens, the atoms literally become electrically charged ions. And, well, since opposites attract, an incredibly powerful electrostatic attraction forms between these positive and negative ions. We're talking about very strong forces here, meaning it takes a massive amount of energy to break them apart. Moving right along to Section 2, forming cations and anions. Now, let's look at the actual mechanics of this electron transfer. What exactly happens to an atom the moment it gives away or receives an electron? Think of it like a real-world trade. Look at sodium. It has just one single electron in its outer shell. It's kind of like wearing a bulky extra jacket that it really doesn't need. And to get down to its stable, full shell underneath, it needs to ditch it. Chlorine, on the other hand, has 7 outer electrons. It only needs 1 more to complete its shell. It's basically freezing and desperately needs that jacket. So by transferring that 1 electron from sodium to chlorine, both achieve a perfect, stable, noble gas configuration. Sodium is left with a positive charge, chlorine gets a negative charge, and boom, they lock together. Okay, you are definitely going to want to screenshot this summary table, because getting these terms mixed up is a remarkably common recurring error on exams. You've got to remember that metals lose electrons to become positively charged ions, which we call cations. Conversely, nonmetals gain those electrons to become negatively charged ions, known as anions. Seriously, just keep repeating to yourself, metals lose and become positive, nonmetals gain and become negative. So, how does this look on a larger scale? Let's find out in Section 3, the ionic lattice structure. Let's see how this builds from a single pair of ions into a massive 3-dimensional structure. Because in the real world, you don't just have one single sodium atom and one single chlorine atom reacting in a vacuum, right? You have millions of them. The electrostatic attraction isn't just a straight line between 2 atoms, it happens in literally every direction. Every positive cation is magnetically pulled toward all the negative anions surrounding it, and vice versa. This causes the ions to pack tightly together into this huge, regular, repeating pattern called an ionic crystal lattice. This alternating arrangement is exactly what makes the structure so incredibly stable. And because of this lattice structure, ionic compounds share some very specific properties. If you get an exam question about these, you need to hit these exact points to get full marks. First up, they have incredibly high melting points because those electrostatic forces acting in all directions require massive amounts of thermal energy to break. Second, even though they're made entirely of charged particles, the final lattice is overall electrically neutral. The positive and negative charges cancel each other out perfectly. Third, and this is a big one, they only conduct electricity when molten or dissolved in water. Why? Because that is the only time the ions are actually free to move and carry a charge. And finally, their even distribution creates beautiful, regular crystalline shapes, just like the salt crystals you have sitting in your kitchen. Let's shift gears a bit. Section 4, dot and cross diagrams. All right, let's transition into our practical workshop and tackle the exact diagrams you're going to need to draw on your test to prove you understand this transfer. The dot and cross diagram is an examiner's absolute favorite way to test ionic bonding. The dots and crosses, they just help us keep track of where the electrons came from, though in reality we know all electrons are identical. Now, a massive trap students fall into here is messing up the formatting. Please make sure you draw only the outer shell. It saves you time and cuts down on mistakes. And crucially, listen to me on this one. You must always enclose your newly formed ions in square brackets and clearly write the exact charge on the top right-hand corner. Leaving those brackets out is hands down the most common way students throw away easy marks.
Okay, let's put it all together in Section 5, Tackling Exam Questions.
Let's simulate a real test environment and walk through some worked examples, applying everything we've just talked about. Put your pens down for a second and just think about this before you start drawing. Calcium is in group 2 of the periodic table, so it has 2 outer electrons it desperately needs to give away. But fluorine is in group 7. It only has 1 empty space in its outer shell. So one fluorine atom simply cannot take both of calcium's electrons. How does the trade actually happen?
The solution is actually pretty simple. You just bring in a second fluorine atom. As an examiner, when I look at a question like this, I am immediately checking to see that you drew 2 separate fluoride anions. Calcium gives 1 electron to the first fluorine and its second electron to the second fluorine. Now calcium has lost 2 electrons, giving it a 2+ charge. Each fluorine gained 1, giving them each a 1- charge. And notice how those 2 negative charges perfectly balance the single 2+ charge? It keeps the whole compound brilliantly neutral.
Now for the big one. This right here is a classic separator question used to differentiate the A-grade students from everyone else. Aluminum is in group 3, meaning it desperately wants to give away 3 electrons. Oxygen is in group 6, meaning it only has space to take 2. You can't just match them 1 to 1, and you can't just use 2 of one kind. You've got a mathematical mismatch, so what do?
To solve this, you have to find the lowest common multiple between 3 and 2, which is, of course, 6. This means you have to draw 2 aluminum cations, each with a 3+ charge, resulting in 6 total electrons being given away. To catch those 6 electrons, you need to draw 3 oxygen anions, each taking 2 electrons and getting a 2- charge. 2 times +3 gives you a +6 charge. 3 times -2 gives you a -6 charge. They balance out perfectly. Just ensure every single ion has those square brackets and the charges clearly marked. I highly recommend you print this list out and stick it to your wall. Using the periodic table is your ultimate cheat code for instantly knowing the charges and balancing your dot and cross diagrams flawlessly. You literally don't have to guess. If a metal is in group 2, it's going to lose 2 electrons and become a +2 cation. If a nonmetal is in group 7, it'll gain 1 electron to become a -1 anion. Rely on the groups, balance the final math to reach a neutral charge. And for the absolute last time, please double-check those square brackets. If you can remember that ionic bonding is really just atoms trading electrons to find stability, and you methodically use your periodic table to balance those charges in your diagrams, you are going to absolutely crush this chemistry exam. You now have the theory, the structural knowledge, and the examiner's perspective to succeed. So next time you look at a simple grain of salt, I want you to ask yourself, can you visualize that invisible electrostatic lattice holding it all together? Keep practicing those diagrams, and I will see you in the next explainer.